It was discovered in the early 1820s that the presence of a current in a circuit can deflect compass needles nearby. This implies that current generates a magnetic field. As might be expected, the shape of the field depends on the path of the current. So now we'll explore the big book of current-induced magnetic fields. Our first one is a long straight wire just carrying a steady current. And here we have some iron filings down on a piece of paper pierced by that wire, and we can see that they seem to form sort of circular patterns. Or we can have a circular loop of wire, like a little ring of wire, and again piercing a page, and we see what happens, and we get field lines that look sort of like this. And artist interpretation of these are like this. The way they fall off we'll talk about later, the fact that they're denser close by, which makes sense. The field would be stronger closer to the wire. And likewise, where the field is concentrated in here and is stronger than outside, we get kind of these patterns. All right, a series of current loops that share a common axis and are relatively tightly packed is called a solenoid. Solenoids are important because just as capacitors constrain the electric field to be internal, solenoids constrain the magnetic fields to be internal. They are the magnetic counterparts to capacitors, and we can see the field for them is very much concentrated inside and much weaker outside. And again, we'll come back and talk about that in more detail a little bit later. Field lines due to a permanent bar magnet are also circular. All right, so we've been having the field goes out here, comes back in, and then it turns out goes through the bar and then out again. All right, they continue inside the magnet to complete the loop because there's always loops. All magnetic field lines are circular because there are no magnetic monopoles. It's worth taking that away. All right, field lines can only start and end on individual charges. At least for electricity, we have that, and there's no equivalent for magnetism. So there's no place for a magnetic field line to start or end. They must all be closed and closed loops. Let's look a little more closely at the long straight wire. We can figure out where the magnetic field points by using one of the many infamous right-hand rules. Take your right hand and put your thumb along the direction the current flows. Then wrap your fingers along the wire to indicate a circle, and your fingers are curling in the direction of the B field around that wire. Often, because magnetism is intrinsically three-dimensional, we'll often have fields or currents perpendicular to a particular plane where interesting things happen. So we use these diagram conventions to indicate direction. If we have vectors going into the page, for a field we put a whole bunch of little x's, and for a current we put like an x, and we usually circle it to protect it because there's only one of them. If the vector is coming out, we have like a field coming out of the page, we have just little dots. And if current's coming out of the page, we have a dot, but again, we can protect it with a circle because it'd be hard to see otherwise. These are kind of meant to evoke the arrow's tip coming through the back of the page or the fletching disappearing into the page as it flies away from you. All right, so this is just a cute convention we have. Ran across it in mechanics a little bit, but now it becomes very common because we really can't dodge the three-dimensionality of magnetism. All right, the right-hand rule works for current loops too. We curl our fingers around the loop with our thumb in the direction the current's going. Notice here that dot means the current's coming out of the page, and that X means the current's going into the page, so the current's going like this, like loop. And when we curl our fingers, we see we get a field line that looks like this, or up here, down here, we get field lines that look like this, and on the side, they're kind of going sideways. If we're looking from the side of the loop, all right, so we're seeing the whole loop face on, then we can see the current is rotating like this, and inside the loop, all the field lines are coming out at us, and outside the loop, they're all going into the page. Since the solenoid is made of many coaxial loops, the right-hand rule works for it as well, as you'd expect. But notice that the field is much stronger inside the solenoid because every field line that's outside must squeeze together to get in here so it can close, right? Because all field lines are closed. All right, let's try this out. A compass is placed above a long wire. When a large current is turned on, the current shown. In which direction is the compass point? Well, we take our right hand and we say the thumb is pointing that way, so our fingers are going to curl sort of like that. So when we're above the wire, the field is pointing that way, so the field should line up like that. Here's an attempt to overlay the field diagram we have with the wire we have here. There's a break here because this is just clip art. And we can see the field line is circling like this, so at this point it is pushing upward, as we said. The unit of magnetic field strength is called the Tesla, but again, it's an unreasonably large unit, so we tend to run fields of millitesla or even microtesla. The field surface at the surface of the Earth is 50 microtesla. Even on the surface of the Sun, it's only something like 1/10 to 1. If you get really close to a good rare earth magnet or a strong MRI, you might get 1 Tesla, but generally you don't tend to see strengths in the many Tesla. Just because, again, this is coming down to the way we end up defining current, move so much charge around that we get staggering amounts in these other things. The units are unreasonably sized for human beings. All right. Later on, we'll go into more detail where this comes from, but the fundamental magnetic field we'll deal with is the field near a long straight wire, and that's given by that the field B is some constant times the current over 2 pi r. And a lot of things going on here. It's not surprising that the current is here. The stronger the current, the stronger the field we would expect. And of course, current of 0 gives us 0 field, which is what we want. This thing, mu naught, is called the permeability of free space. It's a measure of how easily magnetic fields go through the space. It's kind of analogous to epsilon naught from electric fields. Matter would have a different permeability, so there'd be a different mu instead of mu naught, just like we could have done with dielectrics, that there was a different epsilon instead of epsilon naught. Have we overused mu as a symbol in physics? Yes, we really have. There's too many things that have mu. Here, of course, is meant to be m for magnetism, right? Mu and m for magnetism. The current best value for mu naught is 1.26 times 10 to the minus 6 Tesla meters per amp. That's just about 4 pi times 10 to the minus 6 Tesla meters per amp, and that was originally defined because of this 2 pi r. The 2 pi r is probably also striking you as like, that's a little weird. Why not just roll a 2 pi into mu? And the general answer is that that's a geometric thing. Later on, we'll see when we do Ampere's law that we'll often be taking a integral around a path loop, and so we'll get this circumference 2 pi r, and that's why that showed up in that fashion. Could it be done differently? For sure, but this is the convention we go with now, so we're kind of stuck with it. All right, so a wire carrying 10 amps of current has a field at 1 centimeter, which is 4 times as strong as the Earth's. How far from the wire would a point feel equal magnetic forces from the wire and the Earth? Here, there's a lot of stuff going on, a lot of numbers thrown at you, but it doesn't really matter. If currently it feels 4 times when it's at 1 centimeter, then it will get weaker as we go further out, and we want to get down by a factor of 4, so we need to get further by a factor of 4. It will be at 4 centimeters. A long straight wire carrier's current I is shown. Show the magnitude of magnetic field at the given points based on that point A is 4 of these little lines. Well, again, we have that I is proportional to 1 over R. So, for instance, B is twice as far, so it's only going to have half as much. C is exactly as far, so it'll have the same amount as A. E is also exactly as far, so it'll have the same amount as A. And D is is half as far, so it's going to be twice as much. So something like this. Drawn a little bit nicer, but the same explanation. As with the electric field, magnetic fields add linearly in a vector sense. They superpose. So the total magnetic field at some point is just the sum of each of the individual magnetic fields at that point, but again with vector information included. So what does the direction of the magnetic field do only to wire 2 at point P? We see, using our right-hand rule, if our thumb is pointing this way, our fingers curl like this. So at point P, it would be coming out of the page. Now, what is the direction of the total magnetic field at point P? Well, we can see that we have out of the page from wire 2. For wire 1, we have, since our thumb points that way, our fingers curl sort of like that, which is into the page at point E. But wire 1 is closer than wire 2, so it's also stronger, so there's more into than out. Therefore, the sum is into the page. Right, same setup. If the current is 5 amps, what is the strength of the magnetic field at P as measured in Tesla? Well, we can figure out the field strength at 1 by just running those numbers in, and we find it's 1.25 times 10 to the minus 5th Tesla, about 1 1/4 of the Earth's field strength. The fields from 2 being twice as far away would only be half as strong. And then they're opposed, so when we add them, they would be the half as strong, but in the other direction. All right, the geometry of field around a current loop is much more complicated, but the expression for the field at the center is relatively easy. It's that the magnetic field is mu naught times I over 2r, where r now is the radius of the current loop. So we should be careful about that. Not how far we are, but really, again, I guess how far we are from the current loop, but now we're talking about inside the loop. Note that looks a lot like the long wire case, but there's a weird factor of pi missing, and again, that's a geometric argument that will come from doing some integrals later that is kind of not worth worrying about, but you do need to remember. If we had a flat coil of n loops, in other words, they would just sort of stack right on the other, but they're very thin, then we get n times as much current coming out, so it would be mu naught times n times I over 2r. A solenoid produces a uniform field within its coil, in the ideal case, just like before. The radius of the solenoid turns out not to matter for the field strength, just as the electric field between capacitors doesn't matter on their separation. Instead, what matters is the number of turns per unit length. The more densely packed the turns are, the better their field adds, essentially. For a solenoid of length L with n turns, the field is B is mu naught times n times I over L. Often actually written as mu naught I, and then we have the turn density n over L. And sometimes people will give you little n, meaning the turn density. And that's not entirely standard, but not entirely unstandard. All right, an investigator has made a solenoid by wrapping 100 turns of wire on a tube that's 10 centimeters long and 2 centimeters in diameter. The power supply is providing as much current as it can, but a stronger field is needed, so the solenoid must be rewrapped. Which of the following would result in a stronger field? Wrapping 100 turns of wire on a tube that's 20 centimeters long and 2 centimeters in diameter. Here we've increased L, but we've not increased N, and we've not changed R, which doesn't really matter. A longer L is bad because we know that the field is mu naught I N over L. So more L is not good. So this one's out. Wrapping 100 turns of wire on a tube that's 10 centimeters long and 1 centimeter in diameter. Well, we haven't changed L, but we haven't changed N, and we know there's only two things that matter, so that one's out. So by process of elimination, it must be this one, and that's because we made the tube shorter, which makes the field more concentrated, so we get more.